Hi everyone, welcome to the second part of our series on understanding transformers from scratch. In this, we will be going through Attention is All You Need paper, and I'll be guiding you through how you can start implementing machine learning paper all by yourself. I believe this is an excellent paper for introduction and for people who want to begin getting into machine learning and want to start implementing machine learning papers. So let us begin. So the first and absolute thing that you must do now that you're living in 2025 is you first need to go to your LLM of choice. For me, that is Claude. You can use ChatGPT or DeepSeek, whichever model you like, which you prefer. And you have to give it a prompt and make it your paper partner. So someone who reads the paper with you, whom you can ask questions, whom you can discuss ideas with. So this is my practical prompts repository where I have kept a bunch of prompts that I use daily, and one of them being the research paper partner. So I'll just give this to Claude along with the paper. So I'll just quickly download the paper. Yes. After downloading the paper, I'll give it to Claude. And then now I have a partner who will help me out anytime I run into any problems while reading the paper. So now let us begin. Attention is All You Need was one of the most groundbreaking papers in NLP, and this was the foundation that led to formation of transformers. So let us begin. Anytime you start reading a paper, you will encounter something called an abstract. An abstract is basically a summary that talks about the whole idea of the paper. So it gives you the introduction, like why this was made, the short methodology that they followed, like the methodology that they followed in short, and the results. So if we have a look, the dominant sequence transduction models are based on complex recurrent or convolutional neural networks that include an encoder and a decoder. Phew, that one sentence itself was so complex that you could write a paper on that, right? Um, but worry not, this is something that you will encounter in a lot of papers, not just in machine learning, that they use a lot of jargon. So, this jargon is meant to get a lot of ideas through machine learning practitioners at once. Now, anytime you run into a sentence that does not make sense, just copy that sentence and give it to your partner. Now, like I searched, what does a sequence transduction models mean? And then the model told me that a sequence transduction model is basically one that translates one sequence into another. Now, why do we want to do that? Because the original Attention is All You Need paper was built for machine translation, i.e., from translating from one language to another. That was the objective that they were trying to fulfill, and that was the very reason that this was made. So what they are basically trying to say here is that most of the current language transforming models are based upon RNN neural recurrent neural networks or convolutional neural networks that have an encoder and a decoder. And the best ones that have performed so well have an attention mechanism. Now, this is very important. A lot of people think that attention was introduced by this paper. That is not true. Attention is an old idea. I believe it was introduced in 2014. Like, that's the most recent, most important one that I remember. So, it's called additive attention, um, 2014. Yes, it was introduced by Mitri Badanu. I apologize if I messed up that name. It's not my local lingo. So, neural machine translation by jointly learning to align and translate. So, I believe this was the first paper that introduced the idea of attention. So, this is a very familiar looking diagram, right? So, they talk about attention and how it can be applied, and specifically additive attention, not the scaled dot product attention that we are aware of. It's a very interesting paper. You should give it a read after you're done with Attention is All You Need. So, let's go back here. Now they are saying we propose a simple network architecture, the transformer solely based on the attention mechanism. So like the previous models that were based on attention mechanisms had attention and the RNNs or CNNs or even a combination of everything together. Now they are saying that they got rid of all those parts and now they just had the attention mechanism, and using that they were able to get excellent scores in these different benchmarks. Like blue is a benchmark on the WMT 2014 English to German translation task. I implore you to look up blue and how it is calculated. The equation itself is a bit complex, but if you try to think about it, how do you tell a machine that one translation is good or bad? Because for any given English sentence, I can have multiple German translations, right? So blue is very innovative idea in my opinion, and you should have a look at that too. And then they say that they are able to score 41.8 after training for 3.5 days on 8 GPUs, a small fraction of training costs of the best models from the literature. So what does that mean? That any other SOTA model, state of the art model that they knew about, was trained for far longer and costed way more than their whole idea did. So they also mention that we show that transformer generalizes well to other tasks by applying it successfully to English constituency parsing both with large and limited training data. Phew, that was just the abstract. But worry not, it gets easier with time. If this is your first paper, take your time, spend a few weeks trying to understand it and try to implement it. The sooner you take the harder path, the easier it will become for you to read the harder papers. So now let's move on to introduction. Now you can think of an introduction as some introducing someone to the whole idea. So the introduction serves the purpose of an introduction is to serve as a means of telling, okay, this is the problem, these are the kind of solutions that people think of, and this is what we were trying to do. So if we have a look, recurrent neural networks, LSTM, gated recurrent neural networks in particularly have been established as sequence modeling. Numerous efforts have continued to. So yeah, like RNNs have been the absolute best so far. Like that's literally it. That's like one sentence. This paragraph is just trying to tell you that. So RNNs have been goated and they do the best so far. Now they are telling you that okay, RNNs are typically like expensive to train, they're computationally heavy and they take a lot of time. And okay, so this is an important part, and I implore you to read about RNNs as well and how they are able to store information, and they use something called a hidden state. So a hidden state sequentially goes into an RNN. So if you look at the loop of an RNN, so let me show that to you. RNN. So yes, now this is called an hidden state that goes inside an RNN again and then again and again. So it is by nature sequential. So they have mentioned that this inherently sequential nature precludes parallelization within training examples, which becomes a critical at longer sequence lengths as memory constraint limit batching across examples. So what they are basically trying to say is whenever you train an RNN, you have to input the data one by one by one. So you cannot parallelize it. So let's say if I have like 100,000 tokens, I have to send one token after the other. But imagine if we are able to parallelize it. What if we are able to send all those 100,000 tokens at once? That is what the main problem was that they were trying to solve, like parallelize the whole computation. So they also mentioned that recent improvements have been made in computational efficiency through factorization tricks and conditional computation, which while do improve it, they still do not solve the underlying problem of parallel computation. So yeah, this paragraph basically says recurrent models are great, but their big limitation is that they do sequential training, which does not allow us to train our data parallelly. And that is the problem that they were trying to solve. Yes, third paragraph, they mention that attention mechanism has now become an integral part to understanding how sorry, attention mechanism has become an integral part on language translation, but that is used along with different architectures like RNNs and CNNs. There is no single architecture which is solely based on attention mechanism. So in this work, they have proposed transformer, a model architecture which, without recurrent neural networks or relying on any other convolutional neural networks or architecture, just solely relies on attention. And they also talk about how they have used the P100s and trained for 12 hours. And that was introduction. That's it. Yes, sounds surprising, but that's about it. Now let's go to background. Now, what does background do? Background is the section of the paper that tells you about. So, this is the main problem that we introduced you to. So, as we talked about, the problem was that okay, we are not able to parallelize it. There's a computation limitation and all that information, right? So, that was the introduction to the problem. Now, the background talks about what has been done so far to solve these problems. So, solutions to these problems so far. So, the goal of reducing sequential computation also forms the foundation of extended neural GPU. So, again, like even the background starts with telling that they are trying to solve sequential computation problems. And then they mention some architectures and some ways that other people have tried to solve this paper. All of this uses convolutional neural networks as a basic building block, computing hidden representation in parallel for all input and output positions. So, if you understand CNNs and truly understand them, they were made initially for. So they have a lot of reasons why they were made, but one big reason was that they are able to reduce the computation cost in computer vision by a factor of tens or even hundreds. So it was huge, and that is why they were used over here for computational efficiency as well. In these models, the number of operations required to relate signals from two arbitrary input or output position grows in the distance between positions, linearly for conv s to s and logarithmically for bytenet. So what does this mean? So it's basically a convoluted way of saying as the length of the sentence grows, it becomes linearly computational for con s to s and logarithmically sorry about that, logarithmically scalable for bytenet. This makes it more difficult to train dependencies between distance positions. Again, so longer it gets, harder it is to train them. In the transformer, this is reduced to a constant number of operations, albeit at the cost of reduced efficient resolution due to average attention weighted positions. In effect, we encounter with multi-head attention as described in section 3.2. So they said that the problem that as you increase the length of the sentence, the training cost increases linearly. They have figured out a way of solving that in transformers, but there is no such thing as free lunch. So to be able to do this, they have to face a reduced effective resolution due to average attention weighted position. What does that mean? Again, let's ask our LLM about it and they will explain it to us. So, Claude has a feature that I really like is you can give it the kind of style you want. So, a lot of times I just give it concise and it tells me in a quick sentence or paragraph what it means. So, what does this mean? What does this mean? So, this phrase refers to a potential limitation of self-attention mechanisms in the transformer architecture. In self-attention, each position computes weighted averages of representation from all positions in the sequence. When a position attends to multiple other positions and computes their weighted average, some precision or resolution of the information can be lost through this average process. So, if that again does not make sense, you can ask more questions to your LLM to try more sense out of it. Moving forward, self attention, sometimes called intra attention, is an attention mechanism relating different positions of a single sequence in order to compute a representation of the sequence. Oh my god. So, yeah, the jargon does not get easier. But it is again basically trying to say self attention is a way in which we can find relation of different words to or tokens to be more precise to each other. That's it. Self attention has been used successfully in a variety of tasks, including reading comprehension, abstractive summarization, textual entailment, and learning task independent sequence representation. Yeah, I'm not going to explain that. Like, you can just call it like a summary, okay? They make summaries out of it. Reading comprehension, that is literally what we are doing right now. So, we are reading this and we are trying to comprehend it. So, that is reading comprehension. Textual entailment, that's a big word. I'll have to look that up later. But you get that, right? So, they were able to figure out that self attention does not only solve one problem. So, earlier, when RNNs and LSTMs were used, they always had a single objective like POS or NRE. So POS is tagging. So tag the, if it's a noun, it's a verb in a sentence, or you have things like NRE, named entity, NER, sorry, named entity recognition. So you have to find the like speaker, who's the speaker in a whole paragraph and all that. So they always had a single task or just summarization. So summarization is a single task, but self attention was able to do much more than a single task, and that is what they found out. Now, end-to-end memory networks are based on recurrent attention mechanism instead of sequence aligned recurrent, and have been shown to perform well on simple language question answering and language modeling tasks. So, excuse me, again, what this is basically trying to say is they have figured out that attention does really well for question answering stuff, and like LMs are famously known as question answering machines. So yeah, to the best of our knowledge, however, the transformer is the first transduction model relying entirely on self attention to compute representations of its input and output without using sequence aligned RNNs or convolution. In the following sections, we'll describe how the the motivation behind self attention, and discuss its advantages over other models. So that is pretty self-explanatory, and then we can move forward to model architecture. Model architecture. So this image over here is arguably one of the most famous images in all of machine learning, in my opinion. And it captures so much information in one single image that it is absolutely mind-boggling. Like, over here, you have something called skip connections. Over here, you have the multi-head attention, which itself has the scale dot product attention. You have something called positional encoding, and they talk about input embeddings. And over here, you have add and normalization steps. So why is the normalization not done before the feed forward network instead of after the feed forward network? Then you see that they have one encoder side, one decoder side. So much information, so many things packed in one single architecture. Now let's break it down step by step and try to understand it. So most competitive neural sequence transduction models have an encoder decoder structure. Encoder decoder structure. Here the encoder maps an input sequence of symbol representation. So basically the input, so if you have a sentence like my name is Pramod, that is your representation. So you can have, for each word, x1 would be my, x2 would be name, x3 would be is. That is exactly not how it happens. Like, there's a process called tokenization, but for simplicity's sake, we'll just use words to a sequence of continuous representation. So the output is called the continuous representation, the output that comes out of the encoder, and that is Z. So Z1, Z2, and up to Zn. Given Z, the decoder then generates an output sequence Y1, Ym of symbols, one element at a time. So now let's say this is English and we want to translate it to French. So it takes my name is Pramod, translates into a machine learning language, machine language that it understands, Z, gives it to the decoder, and the decoder one by one outputs J, Ma. So it J, Ma, Pel, Pramod, Jamapel, Pramod. So one token after a time. So one word after each other. At each step, the model is autoregressive. Autoregressive means one after the other, consuming the previously generated symbol, token, word as additional input when generating the next. The transformer follows this overall architecture using stacked self attention and point-wise fully connected layers for both encoder and decoder. shown on the left and right side. Now let's try to understand the encoder and decoder layer. So you see this number nx, right? So when I first read about this, I completely ignored that. I did not see that at all. So nx basically means a stack. So it's not a single encoder, it's a stack of multiple encoders. And over here, the nx was decided to be 6. So these are 6 encoders, and over here are 6 decoders. So the encoder is composed of a stack of n equal to 6 identical layers. Identical. Each layer has two sub-layers. So this is one layer, this is another layer. The first is a multi-head attention multi-head self-attention mechanism, and the second is a simple position-wise fully connected feed-forward network. We employ a residual connection, the one I talked about. So this is a residual connection around each of the two sub-layers, followed by a layer normalization. That is, the output of each sub-layer is layer norm x plus sublayer x. So this the original input x. So let's say if it's my. So again, it's not exactly my because this is parallelized. So a vector of x's is sent. So like x vector which has x1, x2, x3 up to xn is sent, and the output from the multi-head attention is added. Then we do a layer normalization on that, where sublayer x is the function implemented by the sublayer itself. To facilitate these residual connections, all sublayers in the model as well as embeddings layer produce outputs of dimension d model equal to 512. So as I mentioned, x is a vector. Now the length of the vector is fixed, x equal to 512. So that is the dimension of the model. And that is what they are trying to say. Um, The decoder is also composed of stack of n equal to 6 identical layers. In addition to the two sublayers in each encoder layer, the decoder inserts a third sublayer which performs multi-head attention over the output of the encoder stack. So you see, like it has another layer of multi-head attention which takes the input from the encoder. So two inputs from the encoder, one input from the decoder. That is very important to see. Like remember that point, which performs multi-head attention over the output of the encoder stack. Similar to the encoder, we employ residual connections around each of the sublayers, followed by layer normalization. We also modify the self-attention sublayer in the decoder stack to prevent positions from attending to subsequent positions. This masking, combined with the fact that output embeddings are offset by one position, ensures that this prediction for position I can depend only on the known outputs at positions less than I. So this might sound a bit complex right now, but as we will implement attention in our next video, you'll see that the decoder side applies something called masked self-attention, where we mask all the information after the current I. So the current token, all the information after that is masked, and everything before that is saved. So we can attend to all the info that we already have. And again, it will become simpler to understand once you see the implementation of how it is done. Now let's talk about attention, the big thing, right? So an attention function can be described as mapping a query and a set of key value pairs to an output, where the query keys, values, and output of all output are all vectors. Always keep that in mind. We never work with like single input output. It's always either vectors or matrices. So the output is computed as a weighted sum of values, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. So if you saw our previous video, you already know that we compute a query and key matrix. Now why it is calculated, I already talked about that in my previous video, so I recommend that you go watch that, and it will make understanding this part way clearer and much easier. So you take qk, mat mule is the matrix multiplication, scale it, so that is divided by under root dk, mask it, mask only if it's in the decoder layer, then apply softmax to it. So softmax is a single function, a pretty simple function, and then you do a matrix multiplication of that with the v matrix. Now this is your scale dot product attention. Now you do it h times. H is defined by the like writer, whoever writes the code. You define how many scale dot products you want, and then you concatenate them, and the go. Yeah, sorry about that. So that is our scaled dot product attention. But when it comes to multi-head attention, we do the scale dot product attention h times, we concatenate that, and then we do a linear operation on that to get a single output matrix. We'll see more of that again in our next video, or you can watch my previous video to understand how this particular step is done. So let's look at the scale dot product attention. We call our particular attention scale dot product attention. This input consists of queries and keys of dimension dk and values of dimension dv. We compute the dot products of queries with all keys and divide each by under root of dk. So that is the scaling. And apply a softmax function to obtain the weights on the values. In practice, we compute the attention function on a set of queries simultaneously, packed together into a matrix Q. The keys and values are also packed together into matrices K and V. We compute the matrix of outputs as attention QKV. These are matrices. So anytime you see a big, so like so Q like uppercase, that means a matrix. You see it in a smaller case, that means it's a vector. So QKV. The two most commonly used attention functions are additive attention, as I talked about initially, and dot product attention. Dot product attention is identical to our algorithm. That means it is very similar to the way they have done it, except for the scaling factor. So they introduced a new factor, that is divide by under root of dk. Additive attention computes the compatibility function using a feed forward network with a single hidden layer. While the two are similar in theoretical complexity, dot product attention is much faster and more space efficient in practice, since it can be implemented using highly optimized matrix multiplication code. Now, if you do not understand how additive attention works, I will link to a blog on that in the description box below, where you can understand more about additive attention and how that led to the idea of scale dot product attention. And it's a pretty nice blog. Like, it's a small part article from a book called dive into deep learning, which is a very nice book in my opinion. I recommend as one of the best books for most beginners to read. Now let us proceed forward. Yeah. While for small values of decay, the two mechanisms perform similarly, additive attention outperforms dot product attention without scaling for large values of decay. We suspect that for large values of decay, the dot product grows large in magnitude, pushing softmax function into regions where it has extremely small gradients. To counteract this effect, we scale the dot product by under root of decay. So what are they trying to say here? That they have seen that the additive uh, um, additive attention outperforms dot product when the input is large, but additive attention does not have the ability of using efficient matrix multiplication. So what might be causing the problem with attention? And they figured out that it might be that doing a dot product scales it exponentially, and by bringing it down by scaling it with under root of dk, they can fix this problem. And that was the innovation behind the idea of scale dot product attention. Now looking at multi-head attention. Instead of performing a single attention function with demodel dimension keys, values, and queries, we found it beneficial to linearly project the queries, keys, and values h times with different learned linear projections dk, dv, d. Oh, I believe one of them should be q. Okay, dk, dk, and dv dimensions respectively. On each of these projected versions of queries, keys, and values, we then perform the attention function in parallel, yielding dv dimensional output values. These are concatenated and once again projected, resulting in a final value as depicted in figure 2. So it sounds very complex, but I'll just take a small section from our last video to show you what actually is going on. So what self attention basically does is that you have your different tokens, and it lets you think about, okay, how are different tokens related to me. So if there's a token boy, boy will start thinking about, okay, so there's a gentleman, there's a lady, and there's a granny, and he starts noticing about the details of the gentleman, the granny, the lady, and so on. Now, a single multi-head attention layer is a single room in one fixed orientation. Now, if you go to room 2, and in room 2, I can change the orientation of these people. So I can keep the lady closer to the boy, and I can keep the gentleman closer to the granny. So now the boy can have a better look at the lady and understand more about her. So, okay, she's holding a notepad. Maybe she's a journalist writing something down. So the idea behind doing multi-head attention was basically that giving different representations that a single representation cannot capture. Now going back to the paper, these are concatenated and again projected, resulting in the final values. Multi-head attention allows the model to jointly attend to information from different representation subspaces at different positions. Exactly what I just showed you. With a single attention head, averaging inhibits this. Multi-head QKV equal to concatenate head 1, head 2, head H multiplied by a matrix WO, which is trained alongside with the model. We will train this again in our next video, and where head I is equal to attention Q, which is multiplied with the matrix IQ, that is for the ith head, K, which is multiplied with the matrix WK, V, which is multiplied with the matrix WV, where the projections are parameters matrices WIQ, which lies in the real domain of real matrix domain of D model into DK, WIK are D model into DK, WIV, which lies into D model into DV, and WO, which W output, which lies in RHDV into D model. In this work, we employ H equal to 8 parallel attention layers or heads. So there are multiple encoders. Each encoder has a multi-head attention layer, and each multi-head attention layer has 8 attention layers or heads. For each of these, we use dk equal to dv equal to d model by h equal to 64. Due to reduced dimension of each head, the total computation cost is similar to that of a single head attention with full dimensionality. So what they are basically trying to say is that we started with 512, right? So 512 divided by 8 is equal to 64, and that is what they figured out. So it is computationally same as doing a single head attention, but by manipulating it like this, you are able to get a lot of different representation that you couldn't get earlier. Now, what are the different applications of attention in our model? The transformer uses multi-head attention in three different ways. In encoder and decoder attention layers, the queries come from the previous decoder layer and the memory keys and values come from the output of the encoder. So it is again very important to understand this part. The queries come from the previous decoder layer and the memory keys and values come from the encoder. So over here, these are the keys and values. The query is coming from the decoder, but the keys and values always come from the encoder. This allows every position in the decoder to attend over all positions in the input sequence. This mimics the typical encoder-decoder attention mechanism in sequence-to-sequence models, such as these different models. The encoder contains self-attention layers. In a self-attention layer, all of the keys, values, queries come from the same place. In this case, the output of the previous layer in the encoder. Each position in the encoder can attend to all the positions in the previous layer of the encoder. So this is important to understand that so far we talked in a decoder you apply a masking, but in an encoder that is not the case. So a token can look at the future tokens as well as the past tokens. So an encoder is able to look at all the information about the sequence, so from the beginning. Now, similarly, self-attention layers in the decoder allow each position in the decoder to attend to all positions in the decoder up to and including that position. So nothing after that, up to that position. So everything before that and that position. We need to prevent leftward information flow in the decoder to preserve the autoregressive property. We implement this inside of the scale dot product attention by masking out, setting to minus infinity all values in the input of the softmax which corresponds to illegal connections. Now moving forward to point-wise feed-forward network. This is a basic feed-forward network. So you can look over here. They are applying a simple ReLU, I believe. Yeah. So it's a simple ReLU activation function, and it's a feed forward network. Yeah. In addition to attention sub layers, each of these layers in an encoder decoder contains a fully connected feed forward network, which is applied to each position separately and identically. This consists of two linear transformation with ReLU activation in between. While the linear transformations are the same across different positions, they use different parameters from layer to layer. Another way of describing this is a two convolution with kernel size 1. The dimensionality of input and output is D model equal to 512, and the inner layer has dimensionality DFF equal to 2048. So, one moment. I'm not sure what this means. Let's again ask our LLM friend what this means. Uh, what is meant by this? So you should never be ashamed of when you run into any trouble while reading a paper. You have your buddy with you, that is your LLM buddy, and you can always ask it what is meant by the anything that is mentioned in the paper. Okay, so the hidden layer has dimensionality of 2048. So a feed forward network. So you have 2048 nodes basically. So it's projected from 512 dimension to 2048. Embedding and softmax. So we'll take a quick break here, and I'll be back and get back to you. Starting from embedding and softmax. Yes. Yes, I'm back. So let us continue. Embedding and softmax. Similarly to other sequence transduction models, we use learned embeddings to convert the input tokens and output tokens to vector of dimension D model. So what they're basically saying is we take the input, so it can be of any length. As I mentioned, so it can be my name is Pramod. My name is Pramod. I live in India. My name is Pramod. I live in India. I'll be pursuing an education in machine learning or anything. So the sentence can be long, can be short, and they use embeddings to convert them into a fixed length of D model. We also use the usual learned linear transformation and softmax functions to convert the decoder output to predicted next token probabilities. So what they are saying over here is using the output from D model, which again is just a vector. How do we get the token? So what is employed over here? They use linear transformation. So that was 2048 that we talked about the feed forward network. So if we go back over here, and then they do a softmax of probabilities to find the token which has the highest probability of being the next token given the previous tokens, and then that they take the output probability and give us the final word. Again, I've talked more about this in my previous video that you can check out. Yes, and uh, in our model, we share the same weight matrix between two embeddings layer and the pre-softmax linear transformation, similar to this paper mentioned over here. So yeah, you can check it out if you want to do that. I won't be doing that in this video, but yeah. And where were we? Yes. In embedding layer, we multiply those weights by under root of D model. So they're basically saying like how the embedding layer was made, and they are using the same embedding layer weights. So they do not change the weight between the encoder and the decoder, and the embeddings models are always multiplied by under root of square root of D model. I'm not sure why this is done. So what do? We shamelessly go back to our LLM and ask them why is this done. So always control CCC and control V one time, right? Why is it multiplied by the square root of D model? D model. Now the LLM will tell you why. You will get that, and if you have more questions, you can ask about it. And most of the times that I have seen from experience, it's always scale compatibility. So you want it to be more the scale should match, or it is either scaling or either to normalize it, so it or like make the computation more efficient and make it easier for training and generalization. So scale compatibility with the attention mechanism. The taught product in the attention mechanism grows larger in magnitude as dimension increases, potentially pushing the software function into regions with extremely small gradients. Okay, so it to make sure it does not become exponentially small, the scaling in the embedding helps ensure that the initial vector magnitudes are appropriate for the scale dot product attention. Balancing the parameter sharing. Since the same weight matrix is shared between the embedding layers and the pre-softmax linear transformation, the scaling helps maintain the appropriate magnitudes with these weights used in different contexts. So makes a bit of sense. Um, Obviously, it can be simpler. We can obviously ask it like, explain it to me like I am a 5 year old. So, in my opinion, in this day and age, it's not about the person who is smarter. It's just about the person who can use an LLM the most in the most efficient way possible. So, let's think about when you're playing with toy blocks. So, simple blocks. If you have a small tower, it's easy to stack more blocks on top. But if your tower gets too tall, it might wobble and fall over. Makes sense. In this computer model, when the words become numbers, we call these embeddings, those numbers can get too big, like a wobbly tower. So we multiply by root d model, which is like saying the magic number to make sure the numbers just stay right. Not too big, not too small. It's like when Goldilocks found the porridge that was not too hot, not too cold, but just right. So under root d model helps us achieve that. Now, I'll be honest with you, these complexity per layer never makes sense to me. I always have to, again, use an LLM, Stack Overflow, Google them, completely trying to understand them. So, now we'll use the vision capabilities of modern language models, large language models. So, we take a screenshot of this, we give it to an LLM, and tell it to explain it to me step by step, along with examples. So you should never be shameful about it. Everyone does it, you should too. If you're not doing it, honestly, you're wasting your time researching that LLMs have already researched, trained over, and have the information. So always ask use an LLM anytime you run into a question that you believe an LLM can answer. So let's try to understand this. um, Layer type comparison, in my opinion, this is a very important step. Some people might say that you can skip this over, but I believe it is very important, because anything that you develop needs to have bounds, right? So it is bounded by reality, and in reality we are either bound by time or by computation. And if you understand them well, you can understand what is the beauty behind different algorithms and why they were made in the first place. So the columns, you have layer type, the kind of neural network layer, complexity per layer, like how complex each layer is, like not exactly complex in the terms that we understand complex, complexity in the big O notation, how computational cost grows with sequence length and other factors. Sequential operations, how many operations must be done in sequence, can't be parallelized. So, like as we talked about RNNs, they must go in sequence one after the other. Maximum path length talks about how many steps information must travel between positions in the sequence. So, when it comes to self attention, complexity per layer is n squared d. Example for a 100 word sequence. So, if there's a paragraph of 100 words with 512 dimension embedding, you need to compute relationship between all word pairs. So 5 million operation. It's n squared because of the n position needs to be attended to all n positions. So like you make 100, then you multiply each token to all of the other tokens. So this becomes n square then multiplied by d. So you get the complexity per layer. Okay, so now you can understand more about how recurrence, how convolution, how self-attention restricted works. So you can look them up and try to understand more about it. But I just wanted to explain how the self-attention is specifically n square d. Now moving forward, positional encoding. This is, in my opinion, one of the most complex parts of self understanding this paper. Even the equation is not as hard as this equation makes it look. So, since our model contains no recurrence and no convolution, in order for the model to make use of the order of the sequence, we must inject some information about the relative or absolute position of the tokens in the sequence. What does this mean? Now that we know transformers are parallel, that they take all the tokens at once, there is no inherent sequence to them. So they do not cannot differentiate the fifth token from the first token. So we have to add some information about how the different tokens are positioned. To this end, we add positional encodings to the input embedding at the bottom of the encoder and decoder stacks. The positional encodings have the same dimension D model as the embeddings so that the two can be summed. There are many choices of positional encodings, learned and fixed. So, like, you can have a positional encoding model which will learn with your model, or it can be fixed. In this work, we use sine and cosine functions of different frequencies. So again, in my opinion, this is a complex idea which takes time to understand. I have a whole video on it. You can watch it over here. And that will really help you understand how positional encodings work and what is the current state of the art positional encoding. So I'll just skim over this part. So POS is the position of the token. I is the dimension. So like which dimension are you looking for? So like 512 dimensions, right? So if you think of it as a vector, there are 512 dimension, and position is the position of the token in this whole sentence. So it's the first token, second token, third token, and I is the dimension. That is, each dimension of the positional encoding corresponds to a sinusoid. So each dimension has a specific value in the sine function. The wavelengths from a geometric progression from 2 pi to 10,000 multiplied by 2 pi. We have chose this function because we hypothesized it would allow the model to easily learn to attend by relative positions, since for any fixed offset k, pe pos plus k can be represented as a linear function of pe pos. Again, I completely understand this is a bit tough to understand, so I'll attach a video and telling you how you can understand it simply. I'll even attach a few blogs that helped me really understand what this means intuitively. We also experimented with using learned positional embedding. So this is a fixed positional embedding instead, and found that the two versions produced nearly identical results. We chose sinusoidal version because it may allow the model to extrapolate to sequence lengths longer than the ones that we encountered during training. So the limitation of a learned positional embedding is that every time you are using it, you training it, you have to train the embedding model along with your transformer, right? So that tries it to the training data that you have. So if it has, let's say, exponentially more data which is of like 100 tokens or 1000 tokens, the embeddings will prefer them over sentences which have, let's say, 10 or 15 tokens, so they'll perform better there. But fixed positional encoding does not have any such bias. Now let's understand why self-attention. In this section, we compare various aspects of self-attention layers to recurrent and convolutional layers commonly used for mapping one variable length sequence of symbol representation to another sequence of equal length. Um, so symbol representation, complex way of saying input. Input to the machine language, z1 z2 is z up to zn, with zi's xi zi lying in the real domain of d, such as a hidden layer in a typical sequence transduction encoder or decoder. Motivating our use of self-attention, we consider three desiderata. One, so I don't know what desiderata means, but I believe from the given context it means factors. So one is the total computational complexity per layer. Another is the amount of computation that can be parallelized as measured by the minimum number of sequential operation required. So in simple terms, it basically means one of the big factors of using self attention is that it lets you parallelize a lot of computation, and that is in essence very good. And the third being the path length between long range dependencies in the network. Learning long range dependencies is a key challenge in many sequence transduction tasks. One key factor affecting the ability to learn such dependencies is the length of the paths forward and backward signals have to transverse in the network. The shorter these paths between any combination of positions in the input and output sequences, the easier it is to learn long range dependencies. Hence, we also compare the maximum path length between any two input and output position in network composed of the different, as noted in, connects all. In terms of computational complexity, self-attention layer are faster when sequence length n is smaller than representation d, which is so essentially, again, like this whole big chunk of paragraph is saying that one big thing about attention is that it does not lose context easily. So one big problem of RNNs was anytime your sentence got longer than 5 or even 10 words. So sorry, it should be other way around. So like 10 words or even 5 words, RNNs forgot what it was talking about. So evolution in that was LSTMs. Now even LSTMs did not grow big, right? So after 100 words, after 150 words, they lost context. But a big thing that they noticed about transformer is that it does not lose context easily, so you can grow it linearly, exponentially, and you'll see that okay, it still maintains context of the words that came earlier rather than the most recent words that have come in the token that it is around. So that is again a big factor of using attention. Now, I'll be skipping over training and conclusion. You can read about that. Training, they are just telling about how they are, like which data set they used, the hardware, and the different scheduling and the hyperparameters that you used, as well as the optimizers. So these are pretty simple ideas that you can go over yourself. Like the big idea itself was the methodology, and reading this and understanding that it's not that tough. A paper looks very tough initially because it's your first time, and a lot of things are very hard for your first time, right? So give it some time, read 5, 10 easy papers. Attention is all you need is one of the most popular ones. You can read the paper on units is a very simple one. You can read papers on GANs. You can read the paper of DDPM. That's a bit mathematically complex one though. So when you have read like 5, 10 papers, you realize it's not really that tough. They all follow a simple formula. You have an abstract, you have the introduction, the background, the methodology, the training, then the results, and in the end they always have a conclusion, tying everything together. So again, you can go through all of this in the end trying to understand it. And I wish you all luck in your journey of learning machine learning, and hope you read a lot of machine learning papers, implement them all. See you in the next video. Thank you for watching.